Hello again, Math 110 class. In this video, we're going to cover section 5.2, trigonometric functions of angles. First, I want you to recall that there are 6 main trig functions, as we'll call them. There's the sine, cosine, tangent, secant function, cosecant, and cotangent functions, right? And so here's how they're actually defined. Maybe you know this, maybe you don't, but let's suppose that we have a right triangle like so, and here's our angle theta. Then we can define the 6 trig functions in the following way. The first thing we're going to notice is that this leg of the right triangle is adjacent, the adjacent leg. This one we'll call the opposite leg, and this right here is the hypotenuse of the right triangle. And so the sine of theta, maybe you can say this along with me, but it's defined to be the opposite leg divided by the hypotenuse. Similarly, the cosine of theta is defined to be the adjacent leg divided by the hypotenuse. And the tangent of theta is defined to be opposite over adjacent. And if you actually work it out, this is also equal to sine theta over cos theta. I encourage you to verify that by just taking this fraction and dividing it by this fraction, and you'll see that you get exactly what I have here. Okay, now we actually have 3 more, the secant, cosecant, and cotangent. So first, I guess I'll do the secant. That's defined to be 1 over the cosine of theta, which just means the reciprocal, that's all that means. And so it's hypotenuse over adjacent. The cotangent of theta is 1 over the tangent theta. And so that's defined to be the adjacent divided by the opposite. And finally, we have the cosecant theta, which is the reciprocal of sine of theta. And that's defined to be the hypotenuse over the opposite. Just flip the fraction upside down in each of the 3 cases. Okay, so now we're going to get to what are known as the Pythagorean identities. And so we're actually going to start over here, and then I'll write them down as we discover them. There's 3 of them. You don't need to really record or write this part down, just kind of watch. So let's suppose we have a right triangle. Then everyone's favorite theorem is the Pythagorean theorem. If a is a leg and b is a leg, then a squared plus b squared has to equal the hypotenuse squared. Right? A squared plus b squared equals c squared. Well, if I divide everything by c squared, let's see what I get. I get a squared over c squared plus b squared over c squared equals 1, right? Well, this can be rewritten as a over c all squared. That's what it means to square a fraction. You just square the top and the bottom individually. And same here. Right? Well, what is a over c? Well, a over c is adjacent divided by hypotenuse. So this is cos squared theta, actually. Right? Well, cos theta all squared. And this is how we write it, cos squared theta. Similarly, b over c is opposite over hypotenuse. Well, that's sine squared of theta, because it's being squared right here, right? So that's where the square comes from, equals 1. And so this is our first Pythagorean and the fundamental Pythagorean identity. And often we write sine squared first, so it's sine squared theta plus cos squared theta equals 1. And this is the main one from which you can derive all the others. Okay? Now if you take this and divide everything by cosine squared of theta, then what you'll get is you'll get sine squared theta divided by cosine squared theta. Well, that's tangent squared theta. Dividing cosine squared theta by itself gives you 1. And 1 over cosine squared theta, well, that will be secant squared theta. And now similarly, if you take this and divide everything by sine squared theta, you'll get 1 plus cotangent squared theta equals cosecant squared theta. Okay, but I would say that the first 2 are probably the main ones. This one, I mean, it's also important, but maybe to a lesser extent. Okay, So that's how we define and derive the Pythagorean identities. All right, so now what we're going to do is we're going to use this, either the Pythagorean identity or whatever you like, to find the trig values of all 6 trig functions. Well, I think we can already find the sine of theta. That's opposite over hypotenuse. And we also automatically, therefore, know the cosecant of theta, which is just the reciprocal, 5 over 2. So it looks like we get those two for free. You could solve for this length if you like. By the Pythagorean theorem, I know that a squared plus 2 squared has to equal 5 squared, right? If I call this length a here. And so I get 25 equals a squared plus 4. So what that tells me is that a squared equals 21. Just solve for a squared. And so a has to be the square root of 21. Okay, well now what that tells me is that, well, I can find the cosine of theta. That is adjacent over hypotenuse, so root 21 over 5. I get the secant of theta for free by flipping the fraction upside down. Don't worry about rationalizing. And finally, I also get the tangent and cotangent. So tangent theta is going to be 2 over root 21. And cotangent theta will be root 21 over 2. Right? Okay. Now another problem that you'll see, especially on the worksheet, is something like this. So we have that we have a triangle set up here. This is a right triangle, and we have x and y are unknown, so we want to try to find those. But we know the hypotenuse is 10, let's say, and we also know that the angle here is 30 degrees. So we're going to get into a little more about trig functions of angles, but let's hold off on that for now. What I want you to do is to turn to page 336 in the book. And there are well-known trig values at the bottom of the page. So what we see is that the sine of 30 degrees, well, that's going to be x divided by 10, right? But in the book, it says that the sine of 30 degrees is 1/2. So on the left-hand side, I just get 1/2, and on the right-hand side, I get x over 10. Well, I can solve this, and so x has to be 5. There's numerous ways to solve that. Oh, well, now that I know that x is equal to 5, I can fill that in right there. Now I could do the same thing also, but now just use cosine, and that would relate y over 10, right? Well, the cosine of 30 degrees is square root of 3 over 2. And so if you solve this, you get y equals 5 times the square root of 3. And that really can't be simplified any further. But there you go, right? So a couple of these problems can be solved just by looking in the book and finding what the trig values of some well-known angles are. All right, moving on, we're going to talk about how to define trig functions for points in the plane. So let's suppose we have a point here, x comma y. Now, you'll notice if I do the following, so let's say I start at the origin and connect this with a straight line to this point, x comma y, then I actually get an angle if I move counterclockwise, so in the positive direction from the positive x-axis, right? So here's how I'm going to define the angle, or the trig functions of this angle that I get. Notice I get a right triangle right here, right? And so I'll call this angle theta. To define the sine of this angle, well, I need this length here, which is the opposite leg. Well, that's just the height of this point, which is y. And I need to divide by the hypotenuse, and we're going to call this r. You'll notice I say here, let r, which is a positive number, be the distance from that point to the origin. So I get y over r. Similarly, the cosine value is going to be this length right here, which is x, right? That's the x-coordinate of the point, divided by r. And now the tangent value will be the opposite over the adjacent, so y over x, I believe. to get the cosecant here, I'm going to flip this one upside down. To get the secant, I'm going to flip cosine upside down. And to get cotangent, I'm going to flip tangent upside down. So I get r over y, r over x, and x over y. And now we need to be careful here. These are all fractions. R will never be 0, but certainly x can't be 0. And then for here, y can't be 0. Here also, y can't be 0. And here, x can't be 0. Right? But now here's how we do it, how we define all these in the other quadrants. So notice this is in quadrant 1. In quadrant 2, it's not this angle we're looking for. We're always moving positively, so counterclockwise from the positive x-axis. So really it's that angle there. But we still define it in the same way. We define it to be, if this is length r here, we define the sine to be y over r. We define the cosine to be x over r, etc., etc. It's just that you'll notice now we're going to be getting some negative answers. And so that's why I have here, you can define them all in the same fashion. So here, you just have to allow the possibility of negative numbers. So now this angle is really big. It's this angle here. So this is my angle theta. Here, this was theta. And now here, this point in the fourth quadrant, well, it wraps all the way around. And so this is our angle right here. But we still define them in this fashion. Okay? And so from this, we can now read where certain trig functions are positive. So let's look here in quadrant 1. Well, both x and y and also r, so all three of those numbers are positive. So any combination we do with these three is going to be a positive number, right? So all trig functions are positive here. Okay, looking in quadrant 2, this is why we count counterclockwise, because that's the positive orientation, right? So quadrant 1, 2, 3, and 4, just a little bit of info for you there. In quadrant 2, which trig functions will be positive? Well, certainly the y values are positive up here, but the x values are negative. So anything with y but not x will be positive here, and that is the sine function, so sine of theta, and also the cosecant theta. These are positive. The rest of the other four are going to be negative. Okay. Coming down here, quadrant 3, notice both x and y are negative. So to get a positive value out of that, I think I need to like either multiply or divide y and x, right? So here tangent theta and cotangent theta are positive. The other four are negative. And finally in quadrant 4, you probably can see the pattern right now. We're going to get that the cosine of theta and the secant of theta are positive. And the other four will be negative in quadrant 4. Okay. So we'll leverage that in just a minute, but let's first do this example here. Let's suppose that I know that the cosine of theta is 8 over 17, and my angle is acute, which means I have something like this, and now the cosine of this angle is 8 over 17. I want to know the other 5 trig values associated with this angle. Well, I get one automatically for free, and that is the secant theta. I just flip it upside down, so 17 over 8. But now to find the other 4, I'm going to observe the following. Well, I have a Pythagorean identity. I know that cos squared theta plus sine squared theta equals 1, right? Cos of theta is 8 over 17. Okay, so 8 over 17 squared is 64 over 289. And so I can solve for sine squared theta just by subtracting this fraction from both sides. And I get 225 divided by 289. And so to solve for just sine of theta, I just take the square root of this value here. And that is 15 over 17. Okay. So here's one of the remaining 4. I automatically get cosecant for free. That's just 17 over 15, right? Now I have 2 more to find. I need tangent theta. Well, if we go all the way back up to the top, so bear with me here. How was tangent theta defined? It was defined to be the sine of theta divided by the cosine of theta. That's one of our just basic trig properties. So the sine of theta is 15 over 17 divided by 8 over 17. And if you simplify this, that's the same as flipping and multiplying the bottom. And so you get 15 over 8. And then cotangent theta comes for free by just flipping that upside down. Okay, so here's our 6 trig values associated with this angle theta. And I know that they're all positive because my angle is acute. So really, I'm up here in quadrant 1. Okay. Now, let's change things around a little bit. So now what we're going to have is tangent theta is minus 3/4, which automatically tells me that cotangent theta is minus 4/3, right? But now the sine of theta is positive. So what we need to find, let's look up here, find the quadrant where tangent is negative but sine is positive. I think that's quadrant 2, right? Well, let's write that down. We know theta must be in quadrant 2. Okay. All right, so now let's use a trig identity, the second Pythagorean trig identity. So I know that tangent squared theta, which is minus 3/4 squared, plus 1 equals secant squared theta. Right. Well, this is 9 over 16 plus 1 equals secant squared theta. 9 over 16 plus 1 is 25 over 16, so just add fractions by finding a common denominator of 16, and that equals secant squared theta. And so what that tells me then is that secant of theta is just the square root of that. Or is it, right? What quadrant? Now keep in mind, theta is in quadrant 2. So looking back to quadrant 2, only sine and cosecant are positive. So in fact, this is negative. It's the negative square root, right? Anytime you take a square root, you have a choice, and in this case, for us, it's the negative. That tells us that cosine theta, which comes for free, is just flip it upside down, so minus 4/5. Okay. We already have tangent and cotangent. So if you like to find sine, we know that sine squared theta plus cosine squared theta has to equal 1. And if we solve this, we get sine squared theta plus 16 over 25 equals 1. So sine squared theta equals 1 minus 16 over 25, which is 9/25. And so sine of theta, well, we have a choice. Is it the positive or negative square root of 9 over 25? Well, it's right here. Sine has to be positive, right? So it's the positive square root. And then cosecant comes for free. All right, so one more example. Go ahead and try this one if you like. But we'll go ahead and start this one together. I know that the sine of theta is minus 5 over 13, which says that the cosecant of theta is minus 13 over 5. That comes for free. So let's go ahead and put a box around those. Okay. Now, secant of theta is positive. So where is sine negative but secant positive? Well, that looks like it has to be quadrant 4, right? So write that down. Theta must be in Q4. All right, so let's proceed. We can find cosine theta by using the Pythagorean identity that sine squared plus cosine squared theta has to equal 1. And this is 25 over 169 plus cos squared theta equals 1. So cos squared theta equals 1 minus 25 over 169. And so what we get is cos squared theta equals 144 over 169. Okay, and so then cosine theta is the square root of that. But it either has to be the positive or negative square root. But remember, theta must be in quadrant 4, where cosine is positive. So this is the positive square root. The only two that we have left to find are tangent theta and cotangent. Tangent is the sine of theta, which is minus 5 over 13, divided by the cosine of theta, which is 12 over 13. And you flip and multiply, and you get minus 5/12. So that's tangent theta. And then cotangent theta is the last one just by flipping tangent upside down. So minus 12 over 5, or 5 over minus 12. So that's the end of this section. For the first half of the worksheet, you'll need to follow the examples like this. And in the latter part of the worksheet, you're going to need to follow these examples here, where we use knowledge of where theta has to be depending on given information, and then use Pythagorean identities to solve.